Hello, my name is Seth Holder, and welcome to my Physics 2212 Lab 6 lab report on magnetic molasses. The purpose of this lab is to see Lenz's law in action as we watch to see how the magnetic flux generated from a magnet falling down an aluminum foil tube, how it slows down the fall of the magnet. This force generated from the magnetism acting upwards caused the fall to take about twice as long as it did without the tube surrounding it. And as you can see our results, you can see that 0.138 and 0.68 is about the difference we got. And that's pretty much how much it slowed down. This is the setup from the lab. We have the length of the tube, the width of the tube, the inner radius, the outer radius, the mass of the magnet, and the magnetic dipole moment that we found through calculations. These are some of the key concepts we use, including the magnetic field of a bar magnet, magnetic flux, Faraday's law, Ohm's law, magnetic force of a loop, Lenz's law, and the momentum principle. And all of these will be used at some point within the lab or within the coding that we did. Just a few more concepts to fully understand it. Why couldn't we use a ferrous tube, for example, a steel pipe? And this is because it contains iron, which may interfere with the falling magnet because of the induced magnet that's created inside of it. And then what happens to the magnet? How does this compare to the magnet falling in free space without a tube? And as you can see from our previous results, the magnet falls much slower in the tube due to the magnetic force acting up against it. This is the first part of the code we have, where we put our measurements and then find the dipole moment using the magnitude and the r hat vectors. Then we have the code part 2, where we are finding the flux of the magnet. We have the third part of the code, where we are finding the magnetic force in the direction, and we were calculating it, and then we were adding that with the magnetic, or not the magnetic, with the gravitational force, so we can get our net force and to see how the magnet is truly moving. And you can see in step 8, we're calculating the velocity and the position and kind of looping through, so we're finding it at each point of time. These are the results of our code. As you can see, after about 0.175 seconds, the magnet kind of stabilizes and finds its terminal velocity where the force of the gravity is equal to the force of the magnetism, and it causes the magnet to just slow its fall and not continue accelerating as it goes down. We have a few what if questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? And as the resistivity reaches zero, the upward force the magnet creates increases and soon results in the magnet having a greater force upwards than the gravity downwards, stopping the magnet from falling on the tube. And I do mean that the force will be greater going upwards until there is no more velocity from the magnet. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? It is possible that the cuts could cause the currents in the tube to not be able to create a good enough braking force for the magnet, and the magnet were to fall if there were no tube surrounding it at all. But this also kind of depends on how far away the cuts are. Depending on the length of the cut, you need more solid of tube just to slow down the fall. And so the further they are away from each other, the greater the force that would be created. And so you could still slow it down some. It just would not be as much as the continuous tube, if that makes sense. Some possible errors that could have happened in this lab. They're mainly human error, just because everything was kind of done by hand. And so there's multiple different human errors that could have occurred. The first comes from the height and I'll say the angle that we dropped the magnet at, because it could gain speed before entering the tube, so the timing would be a little off because you're not fully, fighting the magnetic force. And it could not be perfectly centered, or the angle like could prevent it from having a force directly upwards every time, which is kind of why we did it 5 times and found an average. And there also could have been the error of timing. The time between dropping the magnet and then seeing it leave the tube because it's a solid tube and you're based on reaction time, it could have caused a delay in just timing it and led to some results that were slightly deferred from what we actually got, which is kind of why you can see that the code has it falling for less time than what it actually what we recorded. It just could have been a human error.